Hello everyone, I'm Nassim. The paper that I'm presenting today is titled Scene Labeling Using Sparse Precision Matrix. This is a joint work with Dr. Mubarak Shah in CRCV at UCF, and it's accepted in CVPR 2016. First, let me define our problem. Scene labeling is essentially assigning a semantic label to each pixel of an image. For example, if we have these images and we have a set of labels or classes, we want to assign a label to each pixel in these images and come up with this semantic images. And this is different from object segmentation because we have to also classify stuff, for example, sky, sea, and etc. So the typical approach for this problem starts with segment an image into superpixels, then using some local features and also using some classifiers label these segments. In addition, some methods use smoothing at the end for giving neighboring segments same label. For example, MRF does this. These methods have some limitation. So they ignore the long-range connection between segments. Also, they don't model the contextual relationship between labels. So in our approach, we want to model interaction between labels as well as segments. For this, we have an energy minimization over a graph that this graph, the structure of the graph is captured automatically using inverse of covariance matrix called precision matrix or concentration matrix. So we encode only significant interaction and we avoid fully connected, but still it's beyond only local connection or just spatial connection. So we use local and global information. Here I just want to refresh your memory with some concept that might be helpful for the rest of the talk or presentation. First is covariance that is familiar. So covariance using expectation measures how random variables co-vary or change together. The other concept is correlation. Correlation is covariance normalized by standard deviation, and so the values are between -1 and 1, so it's more proper to find out how random variables correlated or how we can find out if they are influence each other or not. The other concept is precision matrix. So the precision matrix or concentration matrix is the inverse of covariance. And here, the values in precision matrix measures how tightly the variables are around the mean and how they don't co-vary or how they are independent. So the other concept is partial correlation. Partial correlation measures the degree of association between two variables given other variables. So for example, here we want to find how x and y are correlating given z. If we assume R is a matrix of partial correlation, the helpful relation that we want to use here is the relation between partial correlation or independency and the precision matrix. The values in precision matrix, the zero value in precision matrix means that the partial correlation is 0. So here is the example. If we assume that these variables are Gaussian, the partial correlation matrix and the dependency matrix is same. However, we can, even if it's not Gaussian, we can use partial correlation because finding the dependency, it's kind of complex. Here, we assume that we have 5 random variables, y1 to y5, that this connection that means how they are influence each other, how with K they have an interaction. So this is a covariance matrix for this graphical model, and this is the inverse or precision matrix for this graphical model. As you can see, zeros in the precision means there is no edge between those variables. For example, y1 and y3 here, they don't have any correlation or they are independent, so the value in precision matrix is 0.
So it's inverse of covariance, but this is the precision.
Yes. So since using just sample covariance matrix for finding the precision might not be proper, because if we have a high dimensional data and we have limited number of samples, covariance might not be invertible. More importantly, we want to have a sparse matrix that we just want to keep significant interactions between variables, and we want to discard the noisy or irrelevant edges. So here we use graphical lasso that we want, using the sample covariance, we want to estimate a sparse precision matrix using the penalized log likelihood. Here we add the constraint, the sparsity constraint on precision matrix omega. So using the empirical covariance, we can find the omega. And when we have the sparse precision matrix, we can find the structure of the dependency graph between our variables. This is an example of the relation between graphical model and the sparse precision matrix. Assuming this is a graphical model, this is just a sample. We have 9 random variables. The black edges means the special or local connection. The red means negative interaction, and the blue indicates positive interaction between these variables. Here we have a precision matrix of the ground truth that it's a 9 by 9 matrix, and as I said, the blue means positive interaction and red negative interaction, and white is zeros. So it means there's no edge between them, there is no independence, there is no dependency. This is, on the right, you can see this is a sparse precision matrix learned from data. And as you can see, even though it's kind of noisy, but still it can capture the structure of the graph. So for our proposed method, we use, first we start with segmentation, divide images to superpixels, then we use local classifiers. Here we use features such as SIFT, color histogram, color mean, texture features, and so forth. We use random forest classifiers to classify each segment. Also, in addition, we use global retrieval set that we use. In that, we have a subset of images based on the context of the query image that we use just features for that, and we refine the local classifier scores using this global information. So our method has 2 main parts. The first is training. As I said, we segment all training examples, we find the features for all segments, and then we train our local classifiers. And here it's one of the important parts that we want to find this correlation or this dependency between labels in the data set. Then later on in inference, we use this in a pairwise cost. Here we start with the training images. Then we find the data matrix that each column of this data matrix belongs to an image, and each entry is probability of seeing specific label in that image that we use annotated data and the frequency to find these values. So here all random variables are the labels because we want to find the connection between labels. So using the graphical lasso, we can find the sparse inverse of covariance matrix, and using this sparse inverse of covariance matrix or precision matrix, we can build this label graph that it's a correlation or dependency between labels. So we come up with the graph like this. Here y's are the labels, and we see how these labels are correlated. Then the next part is inference. In inference for a test image, again we compute the features. then we find the interaction between superpixels. As I said, we don't want to have fully connected graph between segments, but also we want to go beyond only neighboring segments. We want to find which superpixel are relevant. So we treat each superpixel as a random variable here, and we come up with the graph of the superpixels. And this graph for the unary term, we use classifiers, and we refine the classifier with the global retrieval set. And for the pairwise, we use appearance of superpixels as well as the cost that we find based on the correlation between labels that we found in the training. Then we optimize this and we get the final result. So for the scene graph structure, the structure between superpixel, as I said, we treat each superpixel as a random variable, and we use graphical also for finding that. Here I want to show you why we use the sparse estimated precision matrix. For example, this is on the left, you can see this is an empirical precision matrix that we find based on sample covariance from the data. As you see, it's very noisy. But on the right, this is estimated sparse precision that has more zeros. Here we just discard irrelevant connections, and we can preserve the significant connection. And as you can see, there's a pattern here. For example, it's like around the diagonal. So now as we obtain our graph structure for the query image, we build a CRF over these superpixels, and we formulate an energy function E. This is the unary term, and this is a pairwise term. So I and J, the connection between superpixels, came from the precision matrix omega. So the unary term is a sigmoid function using the confidence from the classifiers. And for the pairwise term, we use the similarity between superpixel. Also, we use the correlation between labels. So different combination of labels get different costs. Here, delta, we formulate delta using the correlation between labels. The rho is defined from the precision matrix. And F is F measures similarity between superpixels using appearance of superpixel, and also R is the relevancy of superpixel. Then we use alpha expansion to optimize this energy function, and we can get our final result of labels. Here I want to show in experiment and result. First, I want to show the label graph for the CIF4 dataset. CIF4 dataset has 33 labels. The labels are like car, building, sea. As you can see, this is on the left, you can see this is a this is a graph label or interactions between labels that we found using sample covariance. On the right, you can see this is an interaction or the connection between labels using sparse precision matrix. As you can see, here we have fewer edges, and we just preserve those that are meaningful and significant. For example, here car and road, they have positive correlation, and field and building, they have negative interactions. So we use this in the pairwise cost, as I mentioned. We assess our method on different data sets. One is Stanford background data set. So using only local classifier, we can get 72.8% average. This is per pixel accuracy. So using the global and spatial smoothing, we can improve that, and using our final result using sparse structure is 84.6, and these are the other methods that compare with. Here I want to show an example how this long distance can be helpful. For example, if you have this image and this is the classifier output, this is the spatial smoothing result. However, since we have this connection between these two superpixels, we can refine the labels, and we can get better result. And instead of building this is road and it's closer to ground truth. And also so forth. These are some examples. For example, here again the spatial smoothing smooth out the tree on the left, but we can preserve it and we avoid over smoothing. The other data set that we tested our method on is SIFT-flow data set. Again, here the results, we can improve the local classifier result using our method, and there is a noticeable improvement over local classifier using our method. And also these are other methods that we compare with. And here I want to show besides these long-distance connections, the relation between labels can make a difference. For example, here, because mountain and road, they have negative correlation, we give, assigning these two in an image, get higher cost. So we can discard that and remove that and get better results. Also, on the other hand, for example, here the building and door, they have positive correlation. So seeing those in an image get lower cost, and we avoid over smoothing, and we can keep the, we can refine it also, avoiding over smoothing. Also, again, here, car and C, they have negative correlation. They get higher cost, and we can smooth the car. So to sum up, we find dependency and interaction between labels as well as superpixel using Sparse Precision Matrix. And also we incorporate global information using long-distance relationship as well as gist features. We avoid over-smoothing. Also, we can just capture the useful structure of the graph and discard irrelevant relationship without using any fully connected graphs. And we got promising results on different data sets. Thank you.